Welcome to a hands-on walkthrough of running state-of-the-art AI image generation entirely on your Apple Silicon Mac with zero cloud costs and zero GPU rental fees. The model we're using is FLUX.1 Schnell, released by Black Forest Labs, the team behind the original Flux architecture. Schnell is a distilled variant. It compresses what normally takes 20 or more denoising steps down to just 4, without sacrificing image quality. The runtime is MLX, Apple's own machine learning framework, combined with mflux, a pure MLX implementation of the Flux pipeline. This matters because MLX operates on the unified memory architecture of Apple Silicon directly via Metal, with zero-copy data movement between CPU and GPU. By the end of this notebook, you'll have generated photorealistic images at 1024 by 1024. Before we touch a single cell, let's make sure the environment is ready. This project uses UV, a modern Python package and project manager written in Rust that replaces pip, venv, and pip tools in a single command. If UV is new to you, I have a dedicated setup video linked in the description. Watch that first, then come back here. For everyone else, let's move. All dependencies for this project are declared in piproject.toml under the dependencies array. Open a terminal in the project folder and run UV-sync. This does 3 things in one shot. It creates an isolated virtual environment at .venv inside the project, resolves the full dependency graph from piproject.toml, and installs every package into that environment, all without you ever activating a venv manually. On first run with a cold cache, this takes around 60 to 90 seconds because MLX and mflux are large native extensions. Subsequent runs complete in under a second because UV caches compiled wheels globally. Once sync completes, now open the notebook in VS Code. In the top right kernel picker, select Python prompt shot. If you don't see it, reload the VS Code window with Command-Shift-P, then developer reload window and check again. That's all the setup. The environment is fully isolated. It won't touch your system Python or any other project on your machine. When you're done, you can remove everything with rm-rf.venv, and the project folder is clean again. Kernel selected. Let's run the cells. Cell 1 handles all imports and performs an early sanity check on the MLX installation. The standard library imports, OS, platform, subprocess, time, pathlib, and warnings, are all bundled on a single line intentionally. These are pure utilities with no side effects, so grouping them keeps the top of the cell readable and signals to a reviewer that none of them carry configuration state. The 2 warnings .filter warnings calls suppress future warning and user warning categories. Both mflux and the Hugging Face tokenizers emit a flood of these at import time. They're informational notices about upcoming API changes, not errors, and silencing them keeps the notebook output clean without hiding anything that would affect correctness. If any of these fail, say the user is running on an Intel Mac or forgot to run UV sync, the accept clause re-raises a clear, actionable import error that tells them exactly which command to run to fix it. This is an important pattern. Never let a missing dependency surface as a cryptic attribute error 3 cells later. The final print statements confirm the installed versions of MLX and NumPy, and crucially print mx.default device. On a correctly configured Apple Silicon machine, this should read device GPU 0, confirming that all MLX operations will dispatch to the Metal GPU and not fall back to the CPU. If you see device CPU 0 instead, stop here. Something is wrong with your MLX installation. Cell 2 handles authentication with the Hugging Face hub. FLUX.2 Schnell is a gated model, meaning Black Forest Labs requires you to accept their terms of use before the weights are served to you. This is standard practice for frontier generative models going through responsible release. The implementation uses Python dotenv to read a local.env file, rather than hard-coding the token directly in the notebook. This is the correct security pattern. Hard-coding a Hugging Face token in a notebook cell means it will be committed to Git, stored in the notebook JSON, and potentially leaked in screenshots. With .env, the secret lives in a file that belongs in your .gitignore and never touches version control. Notice the call to login uses add to get credential equals false. This is deliberate. We don't want the token written into the system get credential store, which would persist it beyond this session and potentially be read by other processes on the machine. The token is held in memory for the duration of the kernel only. The whoami call at the end is a lightweight verification step. It makes a single authenticated request to the Hugging Face API and prints back your username. This confirms the token is valid before you spend time downloading several gigabytes of model weights. It's the difference between failing fast and failing after a 5-minute download on a flawed token. Cell 3 is one of the most technically interesting setup cells in the notebook. It does two things. It guards against running on the wrong hardware, and it tunes the CPU thread environment for maximum inference throughput. The architecture check uses platform.machine, which returns the CPU instruction set as a string. On every Apple Silicon Mac from M1 through M4, this is ARM64. On an Intel Mac, it would return x86_64, and the assert immediately halts execution with a readable message rather than letting MLX silently fall back or crash later. The RAM check reads the physical memory size from the Mac OS kernel via systel hw.memsize, then converts bytes to gigabytes. The assert requires at least 16 gigabytes. Why 16? The FLUX.2 Schnell 4-bit quantized model occupies roughly 4 gigabytes of weight data, but during inference, the transformer allocates activation buffers, key-value caches, and intermediate tensors that can push total consumption to 10 to 12 gigabytes. With only 8 gigabytes of unified memory, you'd hit memory pressure and the kernel would start swapping to the SSD, which completely destroys inference speed. The thread configuration is subtle but important. Cell 4 runs a micro-benchmark that empirically confirms metal GPU acceleration is active before we commit to loading a multi-gigabyte model. This is not optional ceremony. If MLX is silently falling back to CPU, image generation will take 10 to 20 times longer, and you'd have no idea why. And here's what to look forward to. Once this benchmark passes, the remaining cells take you all the way from model loading to full batch generation, producing multiple production-ready images with a single loop, entirely on your Mac. No cloud, no GPU rental. Stick around, because the generation results at the end are worth seeing. This is the distilled, 4-step variant of the FLUX.2 architecture. If you want the non-distilled, higher-quality base model, you would keep the same class but pass model config.flux2 Kleinbase 4b instead. The base model requires 20 or more denoising steps, but produces noticeably sharper details for complex scenes. The quantize equals 4 parameter is critical on a 16 gigabyte machine. Quantization reduces the precision of each weight from 16-bit floating point down to 4-bit integers, cutting the memory footprint by roughly 4 times. The full precision FLUX.2 Klein 4b model is approximately 16 gigabytes just for weights. It would consume your entire unified memory before allocating a single activation buffer. At 4-bit quantization, the weights shrink to around 4 gigabytes, leaving comfortable headroom for the inference buffers, VAE decoder, and text encoder. The model config parameter uses the factory method model config.flux.2 4b. This is important. The config encodes not just the model architecture, the number of transformer blocks, attention heads, and hidden dimensions, but also the Hugging Face repository ID that mflux uses to download the correct checkpoint. Flux.2 defaults to this config internally, but passing it explicitly makes the intent clear and makes it trivial to swap in the 9b variant or the base model by changing just one line. Cells 6 and 7 run single image generation at 1024 by 1024 pixels, the resolution the Flux architecture was trained at, and demonstrate the most important hyperparameter in diffusion inference, guidance scale. Let's walk through the generate image call parameters. Seed. This is the random seed for the initial noise tensor. Fixing it to 42 means consecutive runs with the same parameters produce identical output, which is essential when comparing the effect of a single hyperparameter change, as we're doing between these two cells num inference steps, set to 4. This is the denoising step count. With the distilled Klein variant, 4 steps is the design target. The model was specifically trained via score distillation to collapse the normal 20+ steps into just 4, so going higher does not improve quality. It may actually hurt it by over-denoising. Guidance. This is the classifier-free guidance scale, often called CFG. It controls how strongly the model steers the output toward the prompt versus sampling freely from the learned image distribution. In cell 6, we use guidance equals 1.0, the model's default. At this level, the output is creative and loosely faithful to the prompt. The model has a lot of freedom to express the scene in its own style. In cell 7, we raise it to guidance equals 3.5 on the same seed and the same prompt. At this level, the model locks much more tightly to the textual description. You'll see finer details, stronger adherence to compositional cues in the prompt, and less creative deviation. The trade-off is that very high guidance values above 5 or so can introduce oversaturation and anatomical artifacts as the gradient signal overpowers the image prior. The result object exposes a dot image property, returning a standard pillow image object, which we save to the outputs directory with a Unix timestamp in the file name to prevent collisions. Matplotlib then renders it inline in the notebook, using imshow on a plain axis object with the axis decorations hidden. Compare the two outputs side by side. The difference in prompt adherence at guidance 1 versus 3.5 is the single most important intuition to build before you start crafting production prompts. Cells 8 and 9 generate vertical images in the 9:16 aspect ratio, the native format for YouTube Shorts, Instagram Reels, and TikTok. The resolution is 576 by 1024 pixels. This choice is not arbitrary. Flux was trained predominantly on square or landscape images, and the transformer's attention patterns assume roughly equal spatial dimensions. Going to a full 916 at 1080 by 1920 would put extreme pressure on the 16 GB memory budget and risk kernel panics from unified memory overcommit. 576 by 1024 is the largest 9:16 resolution where both numbers are multiples of 16, the VAE's downsampling factor, and where peak memory stays safely below 14 GB on a 16 GB M4. The shorts prefix on every variable is intentional. These cells are designed to run independently of cells 6 and 7. They don't overwrite the shared prompt, height, width, or guidance variables, so you can freely rerun the standard generation cells afterwards without needing to reset anything. In a notebook environment, global variable pollution is a common source of hard-to-reproduce bugs. Namespacing cell local settings protects against that. Again, We run two cells, guidance 1.0 and then 3.5 on the same seed and the same prompt, to demonstrate the trade-off in portrait orientation. At 9:16, the model has to make harder compositional decisions. It needs to fill a tall, narrow frame rather than a balanced square. Higher guidance particularly helps here, because it forces the model to respect the vertical composition cues written into the prompt. Words like stacked top to bottom or vertical format have a much stronger effect at guidance 3.5 than at the default 1.0. The display call uses fig size equals 4 by 7 rather than the 7 by 7 used in the square cells. This renders the preview at the correct portrait aspect ratio in the notebook output. So what you see inline accurately represents how the image will look on a phone screen. The final cell, cell 10, is the batch generation loop. It iterates over a list of prompts and calls FLUX.generate image once per entry, using the loop index as the seed so every prompt gets a distinct but reproducible starting noise tensor. A key thing to notice, this loop runs synchronously, one image at a time, sequentially. With MLX's lazy evaluation, it might seem tempting to enqueue all three generations in parallel to maximize GPU utilization. But on a 16 GB machine, that would instantly cause memory pressure. 3 concurrent 1024 by 1024 generations need 3 times the peak activation memory, pushing well beyond available headroom. Sequential execution is the correct strategy on constrained hardware. The file naming scheme appends a Unix timestamp to each output path. Note that the timestamp is captured inside the loop in of time. Time is called fresh for every image. This guarantees unique file names even for rapid consecutive writes, whereas capturing the timestamp once before the loop could produce collisions if 2 images finish within the same second. The grid display at the end uses PLT dot subplots with 1 column per image, dynamically scaling the figure width to 6 times the length of saved paths. The safety check, if len saved paths equals 1, axes equals list of axes, handles the edge case where a single element list causes subplots to return an axes object directly instead of an array, which would break the zip iteration. And that's the complete notebook. You've gone from raw hardware validation through GPU benchmarking, model loading with 4-bit quantization, guidance experimentation, vertical shorts generation, and finally batch production of multiple prompts, all running on your local machine, powered entirely by Apple Silicon and MLX. The full source is in the description. Give it a like if this saved you time, and drop a comment if you want a follow-up covering low R-ray fine-tuning or image-to-image with FLUX.2 Schnell.